Hello there, PreCalc. This is for all my happy campers. I've got my happy light on here. So the light shining on this paper is supposed to make you feel happy. So it has that special brand of light like the sunlight. So let's see if you're happy, more happy by the end of this. We're looking at counting principles, and the counting principle is being taught on February 22nd. More counting principles. I left my stand down the car, so I'm trying to do this by hand, so holding it, so it's going to be a little wiggly. So you might want to take your motion sickness medicine before we go too much further. Try to be as steady as I can. We've been talking about permutations, which is a fancy word for arrangements. And we started with three letters, A, B, and C, and we decided that there were 6 different arrangements possible for 3 objects. Then when we added a 4th one, we noticed there was 24. And when I have to correct something, it's going to be wiggly. All right, when I take a 5th object, A, B, C, and D, and E, there's 120. So noticing our old friends coming out to play, if there are n objects, there must be n factorial will be the formula for the number of permutations. So I'm not very steady, am I? All right, we're going to add to this knowledge, counting again. Let's use just more practice on permutations. If we have the letters in the word moo, so M-O-O, but so we can tell one O from the other. I've subscripted them, M-O sub 1 and O sub 2. So as you take notes, do that as well. And I'm going to give you the different arrangements that are possible with M-O sub 1, O sub 2. So we could have M-O sub 2, O sub 1, O sub 1, M-O sub 2, O sub 1, O sub 2, M, O sub 2, M, O sub 1, and which one am I forgetting? O sub 2, O sub 1, M. All right, so we can see then that there is a total of 6 of those. So, however, when I look at those in real life, these are not distinguishable. So, really, in real life, there is no sub 1, sub 2. So let's get this business out of here. There's no such thing in writing as an O sub 1, O sub 2. They just look like O's, the alphabetical O. So let me get these out of here. This is ridiculous. So, all right. So here I have removed the subscripts, which now are gone, and now I see that there are repeats. So we can't really distinguish this moo from that moo. So we can't really count that as a distinct or distinguishable permutation. So this is a repeat of that. So we get one of the doubles out, and this is a repeat of that. So how many did we come up with after all? Instead of the 6, we have been bumped down to just 3. So that's what we're going to look at next, and that is called distinguishable permutations. And I can calculate the number of distinguishable permutations by looking at a formula. The formula works like this. The number of distinguishable permutations. Let me turn this happy light off. It's kind of making a blue haze, isn't it? All right, I don't have good light here this day. All right, I don't know if that's better or worse, but forget about being happy. Number of distinguishable permutations is going to follow this formula. In the numerator, it's n factorial. N is how many objects, and so in this case there were 3 letters. And then in the bottom, we're going to divide by n sub 1 factorial times n sub 2 factorial, n sub 3 factorial, etc., depending on how many different repetitions we have. So what do these stand for? Add some 1, is how many of one kind do we have? And n sub 2 is how many of another kind do we have? And n sub 3. So let's apply this formula to our mu situation, which we know from working it out there were 3. So I'm going to put in 3 factorial on the top. That's how many letters I had. That means whether they're alike or not. So there was an M, an O, and an O. So they get a 3 letters. On the bottom, there was 1 that was M. So there was 1 of one kind and 2 of the other. The 2 O's show up in the formula like that. So 1 factorial can be ignored as it equals 1. And then I calculate that, and you can see how to do that, and I get 3. All right, let's look at another distinguishable permutation problem. Let's look at banana. So we're going to look at all the distinguishable permutations from the letters in the word banana. So what will go on the top for n? Will it not be the number of letters in the word? So I see 6, so I'm going to put a 6 factorial for that. 6 factorial. And then on the bottom, how many letters are of one kind and another? Well, there's only one B, so that would be 1 factorial, which I generally ignore writing. Then N2 would be how many A's? I see there are 3 of that kind, and N's, there are 2 of that kind. So I will put in the denominator a 3 factorial for the A's and a 2 factorial for the N's. Then I calculate that, and the 3 factorials cancel, the 2 goes into the 6 3 times, and it will leave us 3 times 5 times 4. So we get a total of 60 different distinguishable permutations from the letters in the word banana. And your book actually writes them out if you care to look at them. All right, that's good for distinguishable permutations. I'm not sure how long this video is, so I don't want to come near to 15 minutes, so I'm going to shut down and do the second part right now. So see you in a minute.